Okay, welcome back. This is a video discussing the final topic in the organic curriculum package. That's topic 10. This is section 6. This is about reaction pathways. Now, on this one, I'm just going to have to give you an outline, and you're going to have to practice them by looking at old tests. What you're required to know here is how to do these conversions. So commonly, an IB test will say, how would this particular chemical be formed? And it's important that you, first of all, recognize what type of chemical it was, and then once you identify the type of chemical it was, how you could convert it, or how you could make it from what starting point. So the first thing you need to look at is this little chart here. It's quite a mess, and each arrow represents a conversion process. The M's indicate processes where you need to know the steps involved, which is called the mechanism, and the others you just kind of have to know, like the reactants and products. If there is a substituent like a catalyst or something, or the conditions it has to occur under, they also have to be listed. So you'll need to learn those. So I'm going to go ahead and get the simple ones, or simpler ones, out of the way. So let's go ahead and start with, we'll start in the center and we'll work our way out. Remember, we covered these in the alkane video, so I would refer you there. We covered this arrow here, this arrow here, this arrow here. We covered this arrow also. I think we covered, yeah, and this arrow also. So I'm going to go ahead and number those. I'm going to number this arrow number 1, this one number 2, and this one number 3, this one number 4, and we'll talk this one number 5. And I'll do the best I can over here. So number 1 refers to the process of hydrogenation. That is the addition of hydrogen across a double bond. So remember, the most common starting point was ethene. So if we use ethene as our example, excuse me, that should have the double bond there. We add that across the double bond. It adds symmetrically to produce the alkane ethane, as you can see here. No mechanism required. Number 2, in the process of going to making a halogenoalkane. Remember, halogenoalkane is carbon-to-carbon single bonded groups with a halogen attached. So we'll start with our same ethene compound as we did in the alkene video, and we'll add a halogen, a hydrohalogen at HCl, because remember, this is a single halogen attached. You can see at the top dihalogen, which is 2 halogens, so that's a different process. So this is an example where we're adding a hydrohalogen compound, and the products, again, it adds. It's an addition reaction, adds across bond the H from hydrochloric acid would be, we could think of it as being there. So that is the process of forming a halogenoalkane. From that alkene down to an alcohol, that is called hydration, where we add water. Now, this one has special conditions that you need to be aware of. The addition of water typically is in an acidic solution where we have sulfuric acid as a catalyst, so you may be required to state that, and the water adds across the bond, forming an alcohol. In this case, that is a primary alcohol. It's important to understand that. This, if you had the H to one, the OH to the other, that is now a primary alcohol. So you can see that we're going to use alcohols as a starting point. We can form ketones and or aldehydes. So alcohols can undergo various things depending on whether they're primary, secondary, or tertiary. The same thing can happen with halogenoalkanes. When we form them and produce alcohols in the previous video on halogenoalkanes, primary, secondary, and or tertiary halogenoalkanes can undergo different mechanisms. So we're going to keep that in mind for later. For number 4, turning an alkene into a dihalogenoalkane is, we'll start with our ethene again, and this is the addition of a halogen. Remember, they are diatomic, so that would add across the bond. Remember, this is an outline of the process known as bromination. It is a test for alkenes. Bromine is brown, so bromine water is a brown solution. If you add a chemical to it that you're testing to see if it's an alkene or a mixture that you think contains an alkene, if the brown color of the bromine water decreases, that tells you that there is an alkene because the bromine is adding across the bond. Another symmetric thing. It's an addition reaction. And the last one here in this sequence, the polyalkene. Remember, under certain conditions, it's not important what the conditions are. Under certain conditions, we can form polymers of this. So remember, think of it as this bond breaking homolytically and producing, I'll put in parentheses here, producing a free radical. Let me put that up. Let me clear that up slightly so we can see it a little more clearly. So these two H's I'm putting on are the original two, and there's now that radical. There's also the single bond here, and this side would also have that radical. So both sides of this are very reactive, so we could attack a neighboring ethene to polymerize. And so basically you get that symbolism we introduced in the alkanes video, where you get multiple repeating polyalkanes in this case. Or it does say polyalkenes, but that's actually not necessarily true. The only time that would be true is when I guarantee you they're not going to ask you to do that. So this would be a polyalkane, something like this. So we'll leave it at that. Let me go ahead and clear this off of here, and then give us a fresh start here. So we took care of this one, this one, this one, this one, and this one. So let's focus on some of the others. A dihalogenoalkane to a trihalogeno or a tetrahalogenoalkane. That is a process not very common. I really doubt that they're going to ask you to do this one, but if you remember one of the ways of creating a halogenoalkane, especially this one here, from here to here. So why don't we start there? We'll start here and we'll do this mechanism. Remember, it is possible to form a halogenoalkane by homolytically cleaving chlorine using ultraviolet light. And this is a free radical, can react with this compound, producing hydrochloric acid and leaving behind a free radical in its place. Remember, that's a substitution reaction, and this is a chain propagating step. Remember, this is the initiation step. This is a propagation step where we have a free radical producing another free radical, which can then continue to react. So this one could react with one of those same chlorines that is in the area. So that is a method for forming a halogenoalkane. Now there is no reason why that process could not continue. This, because there are other free radicals around, this could continue to react to form trihalogenoalkanes, even tetra, dies, and so on. So that's the process here. I really doubt that they're going to ask you about that. There are other methods for doing so, but we're not going to cover them here. But as a reminder, remember this part here where two free radicals combine, creating no new radicals. This is a termination step. So refer back to the alkane video if you're not sure about that process. So that would be the mechanism for alkane to halogenoalkane. For a full featured listing of it, refer to the alkane video, please. So let me clear that off. So that takes care of that. Let's go ahead and talk about this one, because now we've taken care of that mechanism. We briefly touched on that. Let's talk about this mechanism here. This is the leaving groups that we discussed in the previous video, the 10-5 video. Remember, halogens, I'll use chlorine in this example. Remember, this is not accurate drawing. But chlorines are a good leaving group because they can take these two electrons from this bond, which is a polar bond, and they can leave and be fairly stable as a negative ion. But of course, they'd leave behind, in that case, a positively charged carbon. This is called a carbocation, which is extremely reactive. Now that carbocation can obviously react very quickly because it's not very stable, as I said. So remember, refer back to the previous video just for a little bit of guidelines. The primary halogenoalkanes, for example, this one is primary. They can undergo SN2 substitution. Remember, that's usually with a good nucleophile like hydroxide, and these two collide. This collides with this partially positive carbon atom, allowing this leaving group to leave and forming a bond. This attacks here and bonds, so I'll kind of draw it off kind of cockeyed just to show you that it's there. That chlorine, which was here in this location, has left, and there it is. So because there's two things involved, this is SN2, and for tertiary, remember that occurred by a two-step process. So because the hydroxide group can't get in here very well, it gets close, but the first step before this collision occurs is for the leaving group to leave, leaving behind the carbocation, which I'm going to try and squeeze in here for you. I'll use a little bit of shortcut. And then remember, this process is very slow, so this is the rate determining step. It only involved one reactant, hence SN1 for tertiary. Secondaries can undergo either one. There is no predicting. They can do either one. So that's the mechanism for that. Please make sure you refer to just checking my time there. Refer to the halogenoalkanes video for a full featured rundown of that. So that takes care of that. Now let's finish with our alcohols. Remember that we had primary, secondary, and tertiary alcohols. So refer to the alcohol video for a little bit more. Remember, a primary alcohol like ethanol, when you react it with acidified potassium dichromate, typically with an acid present, we can oxidize that first of all to an aldehyde. And remember, aldehydes have a low boiling point, so we can purify that product. We can stop this process. It would generally continue, but we could stop it here by gently warming the mixture, and this would evaporate, and then we could collect it in another container where we would cool it and it would liquefy, so we'd separate. That's called distillation. However, if we continue to heat it, it's called heating it under reflux, and there was still some potassium dichromate present, we would produce our carboxylic acid. So that takes care of this and this. Remember, that's for primary alcohols only in this direction. In this direction, this is for a secondary alcohol. A secondary alcohol like this one, with acidified potassium dichromate, can be oxidized to form a ketone. This is propanone. Tertiary alcohols do not get oxidized. So that covers all of those steps. You can find them in a little more detail in other videos. Namely, I would look in the alkane video for this one, halogenoalkane video for this one, the alcohol video for those, and the alkene video would cover 1, 2, 3, 4, 5 of these. So look at those at your leisure, and remember, practice the tests. That's where you'll get experience using these, and email specific questions if you have them. That concludes this video.